construction of sponge city facilities on roads should take into account green space inside and outside the red line, road longitudinal slopes and standard cross sections, and the layout of municipal rainwater systems. The design should make full use of existing conditions and reasonably determine rainwater infiltration, detention, storage, purification, utilization, and discharge facilities. When designing sponge city facilities for roads, the following points should be considered. The design of green buffer belts along roads should meet the following requirements. Rainwater runoff from roads can be introduced into green belts by lowering the elevation of the green belts and adding openings in the curbstones. The green belts should include energy dissipation facilities, vegetated swales, rain gardens, and depressed green spaces to purify and absorb rainwater runoff, and these should be integrated into the road landscape. Plants in the green belts should be selected based on the vertical arrangement of the green space, water conditions, and the quality of rainwater runoff. It is recommended to use native plants with strong tolerance to salt, waterlogging, and pollution. Rainwater from parks and rainwater from elevated roads should be collected via downpipes into central green belts, with energy dissipation and dispersal facilities at the pipe outlets, depressed green spaces or rainwater detention and infiltration facilities can be installed in the central green belts. If there is sufficient surrounding green space, it should be constructed in combination with the surrounding concentrated green spaces, water bodies, squares and other rainwater storage facilities and green spaces. When renovating severely flooded areas such as existing underpasses and low-lying areas in urban areas, existing surrounding green spaces should be fully utilized to construct dispersed detention facilities to prevent external water from flowing into the low-lying areas. Sidewalks, dedicated non-motorized vehicle lanes and light load roads are recommended to use permeable paving, and scenic driveways should use permeable asphalt paving with edge drainage systems connected to the rainwater drainage system. Street trees can be planted in paved soil strips and should use permeable substrate materials where conditions permit. Street tree planting can be combined with vegetated swales to enhance the sidewalk's ability to retain and absorb rainwater. Sponge city facilities for urban roads should adopt appropriate anti-seepage measures to prevent rainwater runoff infiltration from damaging the road surface and subgrade, and should comply with Urban Road Pavement Design Code CJJ 169 and Urban Road Subgrade Design Code CJJ 194 and the relevant provisions. The technical requirements for ceiling layers in road structures should comply with the relevant provisions of Urban Road Pavement Design Code CJJ 169. Urban Road Construction and Quality Acceptance Code CJJ 1. and Slurry Seal Technology Code CJJT66. Here is the design process for sponge city construction on roads, which can be divided into the following 6 steps. Comprehensive analysis. Conduct a site survey of the construction area, analyzing the traffic demands for roads, elevated roads, squares, and parking lots, soil permeability coefficients, red line widths, conditions of land outside the red line, nearby water bodies, and other relevant factors. Collection points determine the flow direction of runoff, and catchment areas for roads, squares, and parking lots align with higher-level planning. To determine Sponge City control targets for the area, index calculation based on road traffic capacity requirements. Calculate the widths of driving lanes, bicycle lanes, and sidewalks, and determine the width of green belts based on the functional requirements, traffic characteristics, terrain, and natural environment of squares and parking lots. Determine the area of each functional area in the squares and parking lots based on the catchment area of the existing construction area and the impermeable paving ratio of the traditional design. Calculate the annual runoff volume control rate and annual runoff pollution control rate under traditional design conditions, and analyze the gap with the Sponge City control targets. Technology selection and scale determination based on the gap between the traditional design plan and Sponge City control targets. Calculate the control volume per unit area according to the terrain inside and outside the red lines of roads, squares, and parking lots, and the area of green spaces. Select appropriate Sponge City construction techniques and determine the number and scale of measures that can be implemented. Scheme design based on the selected Sponge City construction techniques, squares, and parking lots. Carry out the horizontal and vertical layout for roads, and propose an overall design plan, review and optimization. Check the indices, and respectively calculate the runoff volume control rate and annual runoff pollution control rate of different design schemes to see if they meet the requirements. Identify and adjust any deviations in the calculations. Design implementation based on the refined Sponge City construction facility content and scale. Carry out technical design and implementation, and propose control requirements and measures to ensure implementation. Urban road runoff rainwater should be collected and transferred in an organized manner, pretreated by interception or other methods, and then discharged into the green spaces within or outside the red line of the road. It should be processed through Sponge City facilities in the green spaces, such as rainwater infiltration, storage, and regulation. The choice of Sponge City construction facilities should be based on local conditions, cost-effectiveness, and ease of implementation, in combination with green belts and green spaces outside the road red line, depressed green spaces, bioretention facilities, and constructed wetlands should be prioritized in the design. The technical connections for Sponge City construction on roads can be referenced in the diagram provided. Next, let's explore some key points in the design of Sponge City features for roads. Tree pits on sidewalks should be designed as ecological tree pits, and permeable pavement should be used for sidewalks. The individual tree pits should be connected to form a continuous sponge body. A depressed green belt can be set between the sidewalk and bicycle lanes, with openings in the curbstones to allow rainwater from both sides to collect in the green belt. Permeable pavement should be used for sidewalks to meet the requirements for controlling total runoff volume. The rainwater inlets can be moved into the green separation belt to also serve as overflow wells, allowing infiltrated rainwater and excess runoff to flow. Into the municipal rainwater drainage system, the green isolation belts between bicycle lanes and vehicle lanes should be designed as depressed green belts, with openings in the curbstones to allow rainwater from both sides to collect in the green belt. Permeable pavement should also be used for bicycle lanes to control the total runoff volume. The design of public green spaces outside the red line of urban roads should meet the following requirements. When the design elevation of public green spaces is lower than the sidewalk, the road slope should guide runoff from the sidewalk within the red line and the area outside the red line into the green space for detention and purification. Pre-treatment ponds, rainwater wetlands, and other facilities should be set up according to the surrounding plot conditions to control runoff pollution. When the design elevation of public green spaces is higher than the sidewalk, storage and infiltration modules should be set under the green space to collect and store runoff from the sidewalk and green space. When urban roads are adjacent to rivers, road surface runoff should be discharged into the river through surface flow or culverts to prevent water pollution and riverbank erosion. A vegetative buffer zone, rainwater ponds, and other measures should be set between the road and the river to control total runoff volume and peak flow rates. For urban elevated roads, permeable asphalt paving is recommended. When the green belt under the elevated road has good conditions for vegetation growth and is sufficiently wide, bioretention facilities can be installed to regulate runoff from elevated and surrounding roads. If the elevated road is in the form of an interchange, bioretention facilities can be built in the green spaces associated with the interchange. Spongicity construction facilities and techniques suitable for roads include permeable paving, ecological tree pits, and other similar measures. Permeable pavements can be classified by surface materials into permeable asphalt pavements, permeable cement concrete pavements, and permeable brick pavements. The structural layer of permeable pavements should consist of a permeable surface layer, base layer, and cushion layer, including sealing layers, leveling layers, and filter separation layers. Design of ecological tree pits. The plants in ecological tree pits should primarily be medium to large woody plants, and the planting soil should be no less than 1 meter deep. Ecological tree pits should be placed on sidewalks with a width of 4 meters or more, and can also be integrated with green spaces in road dividers. Overflow and runoff rainwater should be discharged into the rainwater drainage system. The design of depressed green spaces, including the width of the green space, the depth of the depression, and the arrangement of structural layers, should take into account road structure, soil permeability, plant tolerance to waterlogging, and other factors.